All right, everybody. In this video, we are going to be remembering the definition for multivariable function, and we're going to be talking about several ways that we can visualize these, either by graphing them or by graphing related images that help us understand them. Okay, so first, the multivariable functions that we'll be focusing on are going to be functions from R2 into R. And just as a reminder, in general, multivariable functions are just functions whose input domain and whose output codomain can be larger sets than just R1. So M and N can represent any positive integer dimension. In this video, we'll be focusing on functions that are drawn over here on the left, and these are functions from R2 into R. So the domain is two-dimensional space. There are points in the xy plane, and we can often think of it as an f of xy. And then the output is going to be a single expression in terms of x and y. Now, these functions are the ones that we're focusing on because these functions can be graphed really nicely in three-dimensional space, specifically by taking our third dimension, our z dimension, and letting that represent the output. So saying that our function input values, the x's and y's, give us an output that represents the z value or the height. So in this example, we have the function f of xy equals x squared plus y squared. This is our standard paraboloid shape that we've seen before. And we have this picture on the right is our typical graph for it. So as a reminder, this is a function with two inputs, x and y. So the domain, we could think of it as being the xy plane down here. That's going to be our domain space. And then for any given point, x comma y, let's take, for example, this point here. I'm going to say that is the point, let's pretend that's the point 2 comma -1. So we take that as our input, x is equal to 2, y is equal to -1. And then because f of xy is x squared plus y squared, f of 2 comma -1 is going to be 2 squared plus -1 squared. That is going to be 4 plus 1, and so that is going to be 5. And so we go up here, and then this point on the graph occurs at a height of 5. So specifically, this point in three-dimensional space is the point where the x and y values were 2 and -1, and then the z value is given by the output of the function. And in this case, that's 2 squared plus -1 squared. So that's 5. All right. And if we do this for all of our points, x comma y, we get this paraboloid as our graph. Now, we can use technology to graph multivariable functions relatively cheaply these days, but it is really worthwhile to remember different strategies for visualizing these functions, especially if we don't have immediate access to technology. And the best way to do this, our most standard way to do this, is to create a contour plot out of what are called level curves. So remember, for our level curves, we would have our original function, our f of xy. We would choose a given height that we're interested in. So let's say our height is this value c. And then we would look at the x and y values for which f of xy is equal to c. This would give us a new equation, the equation f of x comma y is equal to c. And that is an equation involving x's and y's. And the points that satisfy that equation form a curve in two-dimensional space. So these are x and y values, or x comma y values, that satisfy this equation. They form a curve in two-dimensional space. Let's take a look at an example to make this a little bit more clear. We'll keep our same function as before. F of x comma y equals x squared plus y squared. And let's take a look at a level curve of a given height c equals 1. And so what you'll notice, we have drawn down here is a picture of our graph that's in red. So in red, we've got the graph of our function. So that was z equals f of xy, aka z equals x squared plus y squared. So that is our graph. And then I've also denoted in blue a given height of c equals 1. So I might call this, let's say, z equals 1, because we're saying z equals a given height c, and in this case, c equals 1. So this is the flat plane of height 1. And what you'll notice is that this plane will intersect the graph, right? You can think about this as just a solid plane that is slicing this paraboloid, and it's going to slice it in the form of a circle over here. The curve that we get is the set of all points where z is equal to 1 and the set of all points where z is equal to x squared plus y squared. In other words, the set of all points where x squared plus y squared is equal to 1. And if we wanted to pull this plane out and look at it just as a subset of the xy plane, so here I'm picturing that entire blue plane has been pulled out and just laid flat on the xy plane, then the curve we get, the intersection, is just going to be this set of points here. It's going to be this circle, and it's the circle where x squared plus y squared is equal to 1. In other words, it is this unit circle. Now, typically, if I'm drawing this level curve, I won't write x squared plus y squared equals 1. I'll have x squared plus y squared as my function written somewhere, and I'll often just put this as c equals 1 to indicate that that is the level curve at height 1. And of course, we can do this for other heights as well. So if I wanted to look at, let's say, not a height of 1, but a height of 2, I would take a plane of height 2. I would intersect it with my paraboloid, and I would look to see what that intersecting curve is. And in this case, it would be another circle. I can pull that out, and if I want, I can draw it at the same plane. Ugh, that was a terrible drawing. Let's try that one more time. This is marginally better. We'll get a circle like this, and that circle would correspond to the places where my function is at height 2. If I could write c equals 2 there. I'll just do one more. If I wanted to look at a smaller height, let's say z equals 0, I would slice this, and at z equals 0, the only point on my graph, z equals x squared plus y squared, that occurs at height 0 is the place where x squared plus y squared equals 0, and that is precisely at the origin, 0, 0. So that can be my c equals 0 level curve. So this level curve is just a degenerate point, but in general, these level curves will be curves in the xy plane. And by plotting many of them together, as we've done here, we create what is called a contour plot. All right, and here we have many level curves plotted together. Now, we've seen some contour plots before, and in general, by looking at the contour plot, we get a sense of the topography of our function. We get a sense of how tall it is at different values, and we can also sometimes get a sense of how steep it is at certain values. So I'll conclude just by looking at an example of a contour plot. Here is a contour plot with a bunch of different c values noted already. And based on this contour plot, we can identify different points of interest. For example, if we look at all the different c values, we see that they are around 0, 1, -1, and so on. And over here at the left, they get as high as 2 and as high as 3. And the c value of 2 and 3 form these smaller circles. So if we're thinking about this as a topographic map describing the graph of our function, we can imagine that our function is forming a little hill of some sort here on the left-hand side. And somewhere in the middle of that circle, maybe right around here, just eyeballing, this is a likely maximum value for our function, probably just a little bit above a height of 3. So we can look at the contour plot and try to find maximum values or minimum values. We can also look to get a sense of relative steepness for our graphs. And so for this, I want to focus on this zone down here. Notice that we have many contour plots, many contours, many level curves that are all very close to each other there. That means in a very small amount of time, our graph is going from a height of -1 up to a height of 0, up to a height of 1, up to a height of 2. Our graph is changing its height very rapidly over a very short movement in the north direction. If we were to go in the direction of the positive, in our positive y direction, our graph's height is getting much higher, much faster. And so this is a place of relative steepness. And we can see that because these contours are so close to each other. So in this way, we can look at these contour plots and better understand our multivariable function. This is just one example of several techniques that we can discuss of visualizing multivariable functions, and we'll get into more of them in the future. So thanks so much for watching. See you all next time.